Oh, as a note, if earlier on the slide deck, right, for earlier today, you guys ran this interactive script, right, dot interact dash day one, right? You just need to run day one. Don't have to run day two. That's for tomorrow's reservation, right? I just had that. So run. If you already ran it and you're still on that node, you're good. You don't have to run it again, right? So on your lot, like if you look at your name, let me see if I can show this here. Yeah. Okay. So I am on my laptop, but when you're on Bridges, it'll have your username and then say like R049, right? R049 is actually a node that you're already running on. So you already have the cores. You do not have to rerun the script. But if you're on like Bridges login 0 or something, then rerun that script so you can land back onto the interactive nodes. Okay? Okay. Maybe as a courtesy, I'll just walk through the top bits and say, just give you a layout, right? So a little bit difficult, but there's a bunch of extraneous functions declared at the top. They're already implemented for you, so you don't have to worry about it. Bad programming style. You should put this in a header file. Include the header file. Okay. So we're going to enter main. Have a bunch of variables, 3 heat sources. We're going to time some stuff, calculate some heat. We're going to start the MPI itself. The run script runs it with like 8 ranks, I think. Has some setup for the heat sources, and then it's going to output. And if it screws up, that's here. Okay, number 1, MPI cart create. So I give you in all of these examples, here's the function you're going to call, right? I wouldn't give it to you if you weren't going to call it, yeah? Is it? Oh, this is like insanely hard to see, isn't it? Blue, Vim. Okay. Anyways, this is insanely hard. It says MPI cart create. You're going to use this function, build it all up, and then pass it. So look at your own source code. And it tells you all the inputs, all that fun stuff that we saw in there, right? Comments are insane. Okay, so to do, right? How big is this dim? What's the dimension of our Cartesian topology? 2. Winner. Okay, dims. Maybe. Let's scroll up. I don't actually remember. Okay. Dims, right? Oh, is it periodic? Yeah, that's here. So if you guys can't see this, but dims. Yeah, so dims is the how you partition the mesh, right? So this, when we actually do com create, or the actual Cartesian communicator with the cart create. Let's see here. Shift. Yeah, so dims itself is an input that we have to figure out. And then I need to specify this more dimension. Okay, 1 second. Okay, for DIMS, I was terrible to you guys, and I didn't give you very good instructions. I reused last year's exercise. So you can't see this, but basically on the input script, if you look at that run script, 2 of the entries are actually how you're going to partition. So you actually tell this problem, I want to partition into 4 by 2, for example, right? So we had 8 process ranks, and in the cart.com create, we need to tell it the processor dimensions, right? How we're going to partition up how many ranks in the X direction, how many in the Y direction. The answer is P, X, and Py, okay? That comes from the setup function above. I need to fix this routine, okay? Yeah, so that wasn't very fair to all of you. Okay, the next one, this is not a periodic domain. So you need to fill out periods, the array, such that it's not periodic. How do you do that? Okay, next, let's not reorder. You could try it with reordering, see what happens. I haven't actually tried it, so we could try it, okay? From there, you have the 4 pieces of information in order to make cart create, right? So dim, dims, periods, reorder. I suppose you could even try it with periodic, right? But for the sake of this example, I made it false, right? So you could try that. Yeah. Okay, right? So that's the top part. Now, the part 2, I'm going to leave you guys to figure it out, right? This is actually like the real thinking about lexicographic ordering. Down below, I have the solution, so I don't want to expose it to you. But when you look at your part 2, step 2, right, you need to use that cart shift to know who's my east, west, north, and south neighbors, ranks, right? So you'll have to call cart shift. How many times do you think you'll have to call it? Yes, what's your question? Twice, oh, okay. I was like, question? No, twice, right? So we have 2 cart shifts. I probably programmed it in there, say call it twice, right? Right? And so you'll have to figure out the ordering of how you put plus minus. There's multiple ways to do it. Positive shifts in the X direction or negative shifts, and which one goes in the east-west variables, right? And then step 3, you'll likely pass those to get your neighbors, okay? The question, I did get asked, are we going to do anything with basically MPI plus X, where X could be a GPU, an accelerator, or like to program a GPU? The answer is no, but the principle is being able to coordinate, right? So, for example, MPI plus X, we could use, MPI plus OpenMP, for example, what they're doing upstairs for programming the GPU itself, right? Distributed memory. Now, the typical way we do this, currently, for example, to make it simple, what I do in that context is I have, say, 10 GPUs. I am going to MPI run 10 MPI ranks and map a rank to a single GPU. And then I pack all the data up. That's a really big chunk of data, which I would not want to process with a single core on a node. Like if I have, for example, on, I don't know, Bridges probably has like 4 GPUs per node, right? Then I'll have 4 MPI ranks. But I wouldn't want to do a problem. There's 128 cores per node that I wouldn't want to process, right? But it makes it easy to map one-to-one rank to a GPU. But it is up to you if you really want to say, hey, actually, we do this in our CFD codes. We actually want to use all of the CPU cores for other things. So we'll actually map, say, if we have 128 cores, we'll use 128 ranks. But then we'll map, 32 MPI ranks to a single GPU. We'll actually pack up data to zip to the GPU to work on the whole thing of 32 ranks. But we carefully pack that information. The reason why we do that is suppose you have your CFD solver working on stuff, but then I have another code that is not written for GPUs that needs to use CPUs. And if you're only using a single core to do all of that data, it can take forever. So it's this really strategic balance, but in a sense, distributed memory and shared memory, they're compatible in a sense, right? There are other occasions. For example, we're not going to talk about, this is MPI3, where I have, for example, a gigantic unstructured mesh that gets read in to this AMR framework. And it turns out they make a copy on every single rank of this, what's called the forest. But in order to save on memory without being able to run problems, we use a MPI shared window, which is a shared buffer in MPI, so that all the ranks on that node can just see one single copy of this data. Because it's just read, everyone just needs to see it on that node. But
is there a reason that you're doing 28 ranks in multiple ranks per GPU as opposed to, say, OpenMP, what would that be, 32 cores?
yeah. The reason why is the other, so in order to do the communication between two graphs, that code does not do shared memory programming at all. It's not implemented for it. Just uses MPI. So if you only had one core or 32, I'm wasting 32 of my cores to process data. So it's the limitations of the software, but eventually we could re-implement it to work.
So if you had a structured mesh, you would do
Yeah.
the other.
Sure.
My code uses structured meshes.
Yes. Excellent. Okay. Okay, so this concludes the session. I'll be around. If you really want to finish it, we'll figure it out. I know there's been some issues like UCX weird things or whatever. Was it UX? I don't know. There's some weird, funky stuff running with the nodes, but overall not too bad. And I, of course, coded some things buggy. Thank you for finding them. Let me know if you have questions. Okay.